So now we're finally going to find a way to solve the apples and bananas problem. And along the way, we're going to find out about a thing called the inverse of a matrix and a method for finding it. So let's go back to that apples and bananas problem. We said that I walked into a shop and I bought 2 apples and 3 bananas, and that cost $8 or euros or whatever my currency is. Then I went into the shop on another day and I buy 10 apples and 1 banana, and I got charged 13 euros for that. So I wrote that down as a matrix times a vector. And I could call that matrix A, and I could call this vector R, and I could call that its output vector S. So A operates on R and gives me S. And what I want to do is I want to find out what R is, what this vector AB is, in order to give me the right numbers for the output vector. Now, let's just think about this matrix A for a moment. Let's see if I can think of another matrix. I'm going to call this matrix A to the minus 1, that when I multiply it by A gives me the identity matrix. And I call this matrix here the inverse of A. Because what it does to A is it exactly reverses whatever A does and gives me just the identity. So if I take this equation, AR equals S, if I multiply it on the left by A to the minus 1 on both sides, well, what I find is that this is just going to be the identity, which is the matrix that does nothing. So when I multiply the identity by R, I just get R. So then I've got R is equal to A to the minus 1 times S, the inverse matrix of A times S. So if I could find the inverse of A, the matrix when multiplied by A that gives me the inverse, if I can find the inverse of A, I can solve my problem, and I can find what my A and B are, and I've solved my apples and bananas problem. Now, hold that thought about inverses for just a moment. So we said the inverse of A times A was the identity matrix. And we'll just park that up there for a moment. Now, I actually don't have to go all the way to the inverse to solve the apples and bananas problem. I can do it just by substitutions. So let's look at a slightly more complicated problem and see what I mean. So I'm going to take a matrix that looks like this. 1, 1, 3, 1, 2, 4, 1, 1, 2. And I'm going to say that I have apples and bananas and carrots, say. Okay, they're not a fruit, but they're another sort of fruit-like object that we eat. And so I'm saying that I bought 1 apple, 1 banana, and 3 carrots, and that cost me, let's say, 15 euros. Another day I went in, I bought 1, 2, and 4, and that cost me 21 euros. And another day I bought 1, 1, and 2, and that cost me 13 euros. Now, the thing to notice about a system of equations like this is that I can, if I take this row off of another row, I haven't changed anything, right? So I know that an apple, a banana, and 3 carrots costs 15. So if I take an apple, a banana, and 3 carrots and 15 off of the next row, I haven't changed anything really about that row. The same for the third row. So I can make this problem simpler by going and doing that. That's sort of a process of elimination. So if I take, if I call this row 1, row 2, and row 3, if I take row 1 off of row 2, then I would have, take row 1 off of row 2, I'll have 0, 1, 1. If I take row 1 off of row 3, I'll have 0, 0, and minus 1. I'd still have A, B, and C. And I've taken, on the right-hand side, I've taken row 1. I've taken row 1 off of row 2, so I've taken 15 off of 21, so I'll have 6 left. And I've taken row 1 off of row 3, so I'll have 15 minus 13 is 13 minus 15 is minus 2. So, interesting. So now I can see that actually minus C is equal to minus 2. So I can multiply that row through by minus 1 here. I'll just change pens. And I've got a solution now for C, that C is equal to 2. So that's interesting. Now I've got what it's called a triangular matrix. That is, everything below the body diagonal is 0. And that's a very interesting sort of matrix. I've reduced it to what's called echelon form. All the numbers below the leading diagonal are 0. Now I can do what's called back substitution. I can take my answer for C here, and I can put my answer for C back into the first two rows. So if I take 1C equals 2, I know that 1 times C here is 2 here, so I can take that off there. And I can do the same, I can take 3 times that off of the first row. So if I take 3 times it off of the first row, I'm going to get 1, 1, 0, A, B, C. And I've taken 3 times the first row off of here, so I've taken 3 2's off of here, so I'm going to get 9. If I take that third row off of the second row, I'm going to get 0, 1, 0. And I've got 2 off of 6 is 4. And I can complete, I haven't changed the last row at all. So now I know that C here is equal to 2. I know that if I multiply that row by that column, I've got just B is equal to 4. And I've got A plus B is equal to 9. But I can take my answer for B back off this first row. So I've got then 1, 0, 0, 0, 1, 0, 0, 0, 1. A, B, C. And I've taken 1B, I've taken 4 off of the first row, so that's 5, 4, 2. So my solution here for my apples, bananas and carrots problem is that apples cost €5, bananas cost €4, and carrots cost €2. And that's solved the problem for me. Very nice. So I didn't really have to compute the inverse at all. But I've only found out the answer for this specific set of, this specific output vector. So we said that this was A times R is equal to S. I've only found it for this specific S. If I did the inverse in a general case, I could do it for any S. I could find R for any S. So what I've done here is I've done what's first elimination. I've taken multiples of rows and I've taken them off of each other to get to having a triangular form where the bottom corner here is zeros, and I've just got ones on the leading diagonal. And then I've done back substitution. Back substitution. Well, I've gone back up of putting the numbers for C back into the first two rows, the number for B back into the first row, and so on, to get my solution to my problem. And that's very nice. This is actually one of the most computationally efficient ways to solve this problem. And it's going to work every time, and it's very simple to understand. We can do it in relatively few operations, so it's really, really nice. And one thing to notice here is that in doing so, what I've done is I've transformed A into the identity matrix here. This is just the identity matrix. This one's on the leading diagonals and zeros everywhere else. So this is going to be a key to a way to find the inverse, which is what we'll look at next.